Okay, this is still section 3.2. We are working our way through linear regressions, residuals. Yesterday we were introduced to what a residual plot was, and today we're going to learn how to construct a residual plot on our calculator. So you're going to see in this box here are all of the steps for what you would need to do. I'm going to be switching over to my calculator, but you can reference this and I'll be kind of talking through these steps here. Okay, here's something that's very important. We're going to do this with example 8. But before you can actually make a residual plot on your calculator, you actually have to run your regression first. Okay, so you wouldn't be able to make a residual plot unless you ran a regression. Okay, remember the residuals are those vertical distances which determine how far off your prediction was from the actual point in the scatter plot. Okay, so here we have an example 8. It says the data below lists the weight in grams of 9 different protein bars, and then the y variable, response variable, is the energy in calories for each bar. Okay, this first question is to find and then interpret the correlation coefficient. Recall the correlation coefficient is the R value. Okay, recall that the R value only tells you the strength and it only tells you the direction. It does not tell you the form. Okay, now when you go to your calculator, you should make sure that your diagnostics are turned on. And I think we talked through this in the previous video. You would want to go into your catalog, you would want to choose diagnostic on, and then press enter. Okay, after you turn it on, you shouldn't have to do that every single time. Okay, so if we're going to get the correlation coefficient, we get that from running a regression. So you would need to press the black stat key, number 1 for edit, and you would need to input all of those weights of those 9 different protein bars down into L1, and then their corresponding energy in calories into L2, which I have already done that here. So if you need a second to do that, just pause this video and input those into your calculator so you can kind of follow along with these key punches here. Okay, once you have that data in, it is important, you should really look at your scatter plot before you make any residual plot. So I'm just going to go ahead and come into the stat plot, second y equals. I'm going to choose plot number 1. I'm going to go ahead and turn that plot on. It looks like I've got the correct type selected. I'm correctly saying my x's are in L1, my y's are in L2. I'm just going to tap y equals here real quick and clear out any old equations that might be in Y1. And then I'm going to press the zoom button and I'm going to choose option number 9, which is titled zoom stat. Okay, here I can see a scatter plot. Okay, now if I look at this scatter plot, it really looks like these are pretty linear. Okay, and so you might be thinking, you know, we don't really need to make a residual plot. The purpose of a residual plot is to determine whether a linear regression, whether a straight line, is the best model to use for these points that are in our scatter plot. Okay? What a residual plot, though, will tell you, it will detect if there is any type of curve here that maybe we don't notice from the naked eye. It will detect that and we will be able to tell yes or no whether a linear model is in fact appropriate. Okay, so here's our scatter plot. For part A to this problem, they're just asking us to find the correlation coefficient and then interpret it. So we're just going to run a linear regression first. You're going to press the black stat button. You're going to bump over to the calculate menu. Instead of choosing option number 4, which is linear regression, I would prefer that in stats you choose option number 8, the other linear regression option. The difference is A is the y-intercept and B is the slope, which is how we typically use those variables in AP Stats. Okay, L1 across from XList, L2 across from Y list. Remember, if you have an older calculator, you are now doing L1 comma, L2 comma, and then you're going to want to put Y1 at the end, and for the newer calculators, we're going to place that across from store regression equation. Okay, you're going to press the black vars button, you're going to bump to the right to the Y vars, you're going to press 1 for function and 1 for Y1, and you will come on down to calculate here and press enter. Okay. All right. Okay, so we can see that this would be our equation, which is actually what part B is asking for. So we would just round the A value to 2 places, the B value to 2 places. Again, take note, you can see up above though, the A is the y-intercept and the B is the slope. Okay. And then for part A to this problem, it wants us to write down the R value. Now, you should not round this up to 1 because these points were not in a perfect straight line. But gee, look how strong this correlation is. Let's go ahead and just carry it out to 4 places, 0.9988. That's how far I'd have to go. Well, I guess I could do 0.999 as well. Okay, so I'm going to go ahead and just toggle back here to my notes. Okay, we're going to say that the R is about 0.99, I'll say 88, okay? And then don't miss this. You always want to make sure you read these directions carefully. It's asking us to interpret. So I want to use context here. I want to say the relationship between, okay, here's my 2 variables, weight and energy. Okay, now think about what R tells us. It tells us, I'm going to say energy of protein bars here, okay, it tells us the strength, and I'm going to go ahead and say it's very strong because, wow, that's really close to 1, and it tells me the direction, and since the R value was positive, that tells me it was positive, and we kind of saw that when we looked at the scatter plot too. It was sloped in that direction. Okay, I'm not going to toggle back to my calculator screen. But if I did, the A value rounded to 2 places would be 69.08. The slope would be 3.23x. Anytime you are writing these regression equations, you always need to define your variables. Keep in mind that hat means predicted. This is my predicted Y variable. So it's the predicted calories. Okay, or you could say the predicted energy. That'd be fine. Okay, and the X is the weight, which is measured in grams. Okay, now it wants us to create a residual plot for this linear model, and then by looking at the residual plot, we should be able to determine if a linear model is in fact an appropriate model to make predictions from this set of data. Now, everything I'm going to talk you through on the calculator, I'm going to be walking down through these steps in this box, but you might want to also just kind of look at those and reference the steps here in the box. So let's go ahead. I'm going to flip on back here to the calculator. Okay, our step 1 in that box said make sure you always run a regression first, because what happens when you run that regression is it automatically stores all of your residuals in a list called resid. Okay, like we have lists like L1, L2, L3. There is a list in the menus of your calculator called resid, and that's where all the residual values are stored. Okay, so step 2 here, it says you can see those individual residual values if you go into your list. So I want you to press the black stat key, press number 1 for edit. Let's move the cursor on top of L3, and we're going to redefine that as the residual list. So I want you to press with the cursor, the cursor, okay. Hang on 1 second here. I'm having some computer issues. Okay, let's see here. Okay. Sorry about that. All right, so with the cursor on top of L3, we are going to press the second button and the stat button, which is really picking the list option. And there you see the typical L1 through L6, but look at option 7. that's where the residual name is. So you're going to pick number 7 and go ahead and press enter, and it's going to fill list 3 with all the residual values, okay? All the residual values. So if you want to see the residual graph, what you're going to do is, let's go into our stat plot. Second, y equals, okay? I'm going to have you go to plot number 1 and just temporarily turn that plot off. That's the original data set with L1 and L2. Go back to second stat plot, choose option 2 for plot 2, turn that plot on. Okay. Residual plots are also scatter plots, so we want to keep that same type there. But remember what a residual plot is. It plots points that are the x coordinate, so that's my L1. I want to leave L1 across from X list, but the y coordinate is the residual values. So we want to define the y list as being the residuals. So again, move the cursor down across from y list, press second and the stat button, and choose that option 7 for residual. Okay, and it'll define the y coordinate of your point as being the residual. Then press the zoom button, choose option 9, and what you're looking at now, is not the original scatter plot, but it's actually the residual plot. Okay, and if you look at number 6 in the box on your notes page, it says, remember, you are looking for no obvious pattern when you look at a residual plot. And if there's no apparent pattern, then your regression line is actually a good linear fit for your scatter plot. But if you see a pattern in your residual plot, then a linear model is not a good fit. And there is definitely a pattern here. I'm looking at a parabola in this particular residual plot. And if you recall what the scatter plot looked like, it didn't really feel like there was a distinct curve there. So I think that's what it's telling us is we were zoomed in so close to a small section of a parabola with the original data set that we weren't able to detect with the naked eye that there was in fact a curve there. Okay, so we're going to say this linear model is not appropriate. And we have to give a reason, okay? It says why or why not, okay? Because there is an evident pattern in the residual plot, okay? A residual plot, the purpose of it is it helps us evaluate the appropriateness of a model when the naked eye might not be able to detect that patterns exist in the scatter plot. Okay? All right. So what you guys need to be comfortable with, because I've seen this before on some free response questions on the AP test, is interpreting some computer output. Okay? And so what I have here, and I want you to focus just on the left side right now, is with this computer output, you need to be able to make sure that you can locate the slope and the y-intercept from the computer output. Okay, right now I want you to be able to focus on those two things, the slope and the y-intercept, because if you have those two things, you can build your regression equation. Okay, so here's where these things are located. Okay, when you're given this computer output data, what it will tell you is one of your rows is called constant, and that constant means your y-intercept, okay? Your y-intercept is your constant in your equation. The other row is going to be defined as your x variable of whatever the context of that problem is, okay? So in this particular problem, let's see here. I guess they didn't fully tell us what the x is, okay? But what I'd like for you to look at here is in this column titled coefficient here, okay? This 3.5051, that is the y-intercept, And then this is your slope, okay? So whatever NEA change is referring to in this problem, that's what your explanatory variable was. And I guess we're not really told what the y variable is, okay? But when we would build those two things, we'd put a y hat, and ideally you would have some context and you would define your variables. Okay, so let's try this with example 9. Okay, I'm going to just pinpoint where the slope is and where the y-intercept is. Okay, keep in mind right here, age, that is my explanatory variable. Okay. And just think about it like this. When you write your equation, the number in front of your x, your explanatory variable, that is the slope. And so the row that holds the explanatory variable, the very next number here, that is the number that goes in front of that explanatory variable. That is your slope. Okay, so I'm just going to draw an arrow to that and say that's my slope. Okay, and then this one right here, this is the y-intercept. So I'm going to pull those two values, and let's see here. We're going to go ahead and say y hat equals, and then I'm going to put my, it doesn't matter the order you put these in. This will be my y-intercept. I'll put that first. Oh, and then it looks like maybe my slope is negative, so I'm going to do minus 1.1270x. Okay, I don't have a way of defining this because I'm just going to say not given, but it definitely would be the predicted y value. And this looks like that would have been age. Okay, all right, let's go ahead and take a look at this one here. Okay, I'm going to go ahead and highlight. There's my y-intercept. Looks like that would be my slope. Looks like the explanatory variable has something to do with time or duration. Okay, explanatory variable there. And then it mentions up here, it says this is the analysis of interval versus duration. So if duration is my x, I'm guessing interval is my y. Okay, I don't have the actual problem here to look at. Okay, so I'm going to go ahead and set this up. Y hat equals, I'm going to put my y-intercept plus my slope, and then I'm going to go ahead and define this as duration. And I'm going to define this not as interval, but as the predicted interval. Okay, there's going to be some problems on the homework coming up where you're going to be given some computer output data like this. You got to be able to pinpoint the y-intercept and the slope from that. Okay. All right. Let's go ahead and take a look here at the next page. You know, when we run these linear regressions, you get that R value, that correlation coefficient. We know that tells us the direction and the strength, but we also had another value that popped up when we ran a regression, and that was that R squared value. That R squared is called a coefficient of determination. Okay, and something worth noting is once we've determined that a linear model is actually appropriate to use from looking at our residual plot, then the coefficient of determination and S, what we call the standard deviation of the residuals, those two things then tell us how good our predictions are, okay? Here's the best way to kind of look at this. You know, there are other variables that cause some changes to your response variable, okay, or that might help predict it in some way. What the R squared value tells us, okay, is that tells us how much of the changes or variation in your response variable is tied to that specific explanatory variable. Let me give you an example. The amount of time spent studying is not the only predictor of someone's test performance. There's lots of other factors. It could be how much sleep you got the night before, how attentive you are in class, what is your note-taking ability, what's your natural ability, what is your attendance, have you been absent a lot? Okay, so yes, the amount of time spent studying, if that was our explanatory variable, it definitely helps predict what your test performance is, but it's not the only variable. So when you look at the R squared value, for, say, comparing the amount of time spent studying to your test score, you're going to use that to determine, like, that's the percent of variation in your test performance that is accounted for by, I guess I said X was the time spent studying. It's like how much of the Y is being affected by that specific X variable. So here's the template that I want you to use when you're asked to interpret the R squared value. Okay, when you're asked to interpret the R squared value. Okay, so an example of this is, here's body weight, that's my explanatory variable. Here's pack weight, that's my response variable. I'm using body weight to predict pack weight. All right, now, when we run the regression, you can see this is what we got for our R squared value. So I would just move that decimal point 2 places to the right, and I would say, okay, 60.6% of the variation in the pack weight, okay? So how much my Y variable is changing. 60.6% of how that Y variable changes can be accounted for by the linear relationship with the X variable, the body weight, okay? So the smaller the R squared value is, the less impactful the X variable is on the Y variable, okay? So let's go ahead and just see if we can jot down a few of these descriptions here. It says, interpret in a sentence how much variation is accounted for by the X. Okay, here we have an R squared of 0.875, X is our hours studied, and Y is the SAT score. Okay, let's follow this template here. We're going to say 87.5% of the variation in, okay, the variation is always about the Y variable, okay? In the variation of SAT scores is accounted for, or can be attributed to, by the linear relationship with hours studied, okay? I know that there are a ton of interpretations in this chapter. You need to spend some time studying and memorizing these interpretations for slope and y-intercept, and now this coefficient of determination, this R squared here. Okay, here's another one, 52.3% of the variation in, okay, this has to be the Y variable, in alertness score is accounted for by the linear relationship with, and then what's our X? Hours slept, okay? So hours sleeping is not super impactful to a person's alertness score. There are lots of other variables that are contributing to this. The higher your R squared value, the more that specific X variable is impacting it. Okay, so that's what R squared is. Let's take a look at what S is. Okay, this is not the standard deviation of the set of data. It's the standard deviation of your residuals. And the one thing you need to keep in mind is, what is standard deviation? Oh, that's something that measures spread. So we're looking, what's the spread of the residuals? Okay, S represents the typical distance that the prediction is off from the actual. Okay, think about what a residual is. That tells you how far off your predictions are. So if I told you this is the standard deviation of the residuals, then that number is the typical distance that your predictions are off by. Okay, kind of like your error a little bit there. Okay, so here we have a set of computer data. Remember right here, this foot length, that's your X variable. Okay, you can see we have highlighted here, I'm going to highlight the S, that's the standard deviation of the residuals. Okay, so we just talked earlier about how to find the y-intercept and the slope, and now you know when you see this S, that number there is telling you, hey look, when we do our predictions are typically off by 7.95, and then it would be whatever the unit of measurement is for your Y variable. Okay, here's the template for this, yet another template here. Okay, so we're saying, look, when we use this linear model for least squares regression line with x representing, and then you're going to say whatever your x variable is, and y representing whatever that is, you're going to say the prediction. Here's the key wording we typically use when we talk about standard deviation. Our predictions are typically off by, then you say the number, and then you say label it with whatever your y variable is. Okay, so let's do this for number one. They are telling us the y variable, and this is height. So we're going to say when using the least squares regression line with x being foot length and y equaling height, the predictions will typically be off by 7.9512, and it has to be labeled the unit of measurement that the y variable is measured in. Height was measured in inches, so I'm saying inches there. Okay, all right, let's try the next one. When using the least squares regression line with x equaling age and y equaling weight, the predictions will typically be off by, okay, and what does it say? It said the standard deviation of the residual was 13.89 for this, and I'm going to label this whatever the y variable was. It looks like that's pounds. Okay. If you just say the predictions are going to be off by about 13.89 pounds on the AP test, I don't know, you might get a P for that instead of an E because you're not using context. You didn't really totally define what your X and your Y variables were there. Okay. All right, we're going to wrap up with this last page here very quickly. It says how the standard deviation of the residuals change when you alter the data set. Okay. So when the data, remember when we talked about transformations and we said that if you add and subtract a number to all the values in your data set, that only impacts measures of center, mean, median, things like that, and location. Okay. It would take multiplying everything in your data set in order for measures of spread to be affected. Okay. So it says here, when all of the data is multiplied by a whole number, then that causes the standard deviation of your residuals to increase. If you are dividing it then by a whole number, well, then that would cause the standard deviation to decrease. When the data set is added or subtracted, look at this though, the standard deviation, there's no change because standard deviation is a measure of spread and it's not impacted by addition or subtraction like we said right there. Okay. All right. So on this last one here, the computer output data is actually down here at the bottom. Okay, keep in mind here is your y-intercept, here is your slope. Okay, here we discuss this is the standard deviation of the residuals. And something I didn't mention before, but I should now, is there's one other thing that you now could pinpoint in the data set, and that is this R square. That is the coefficient of determination. That is the percent of variation in your y variable that is impacted by that specific x variable. Okay, so we're going to run through this very, very quickly. It says the data is a random sample of 10 trains, and they're comparing the number of cars on the train and the fuel consumption in pounds. So obviously the more cars that a train is pulling, the more fuel it's going to consume. Okay, so number of trains or number of cars attached to the train and the fuel consumption. Okay, rail cars are the number of cars. So that is our X and our Y is fuel consumption. Okay, fuel consumption. All right, it wants us to pull from the computer output our regression equation. Okay, we're going to say Y hat equals. I'm going to grab my y-intercept of 10.677 plus I got the slope here, X. I'm going to call this the predicted fuel consumption, and X is the number of rail cars. Okay, what is R squared telling you? Well, let's look down here at the bottom again. Okay, R squared is this 96.7%. We're going to think of that template there, 96.7% of the variation in, okay, and then we cite our y variable, in fuel consumption, because there could be other variables at play affecting the fuel consumption, but a large percent, 96.7% of the variation in fuel consumption is accounted for by the linear model with number of rail cars. Okay, that's your x. Okay, it asks us to define and interpret the slope in context. Okay, so the slope is the 2.1495. Okay, remember slope, you might have to look back at your notes to get this template here. This is good practice. For every one, this is our x variable, rail car increase. Okay, so every extra rail car that's added to the train, the fuel consumption increases by 2.1495 pounds. Okay, does this have a practical interpretation? Yes. Okay, that makes sense. Okay, that they're going to use on average 2.1495 more pounds for every additional rail car that they add on. Y-intercept. Okay, the y-intercept is, let's see here. That is our 10.677. Okay, we're going to say when the rail cars are 0, you know what I should have put in here? The predicted fuel consumption is 10.677 pounds. I feel like I should put the word predicted in front of that as well there. Okay, and then the S finally. What is the S telling us? That's this right here. Okay, we're going to say when using the least squares regression line with x being number of rail cars and y being fuel consumption, the predictions are typically off by 4.361, and this is measured in your y